Hi all, my name is Michael. Over the course of the next 10 minutes, I'm going to talk about indexes, particularly indexes in SQL Server. So I'm going to discuss what indexes are, why we should care about them, their potential downsides, and go over a little demonstration. So without further ado, let's go. Let's get this done. Okay, sweet. So in SQL Server, when we create a table without the use of constraints or any other indexes, the data structure that's used is a heap. Now, a heap is similar to my bedroom floor in the sense that it just gets thrown with data, that being my clothes, so long as there's space. Now, the problem with this is the data that we have over here isn't sorted at all. So if we want to select anything, we need to go through each and every record to find the row in the table that we need. Now, this is costly. Although in certain instances, this may be useful. When we're using queries to select from a table on a regular basis, we want an alternative to do this more efficiently. This may be achieved through the use of indexes. Now, okay, that is not, there we go, sweet. This may be achieved through the use of indexes. Now, indexes are a structure used to enhance the performance of various queries. This is accomplished through the use of a balance tree, otherwise known as a B tree. Now, what I'm going to describe here is a clustered index. Now, a clustered index consists of three components: the leaf node, the intermediate levels consisting of one or more intermediate nodes, and the leaf nodes over here, which store the actual records in our table. Now, a clustered index is really, really important as it defines the order of our records as they're stored in memory. Now, how this improves the performance of queries is taking that search that we did using the heap that I mentioned earlier on from linear complexity to logarithmic complexity. And this is achieved through an operation called a scan. Now, a scan is when you traverse from the root node to the leaf nodes to attain records next necessary. So I'm quickly going to show you an example of code. Sweet. An example of a table I created earlier. It simply stores player scores. Nice, sweet, simple, lot of records. Exactly what we need. Now, this over here doesn't have any indexes so far. So what we're seeing is a heap. Although we see that it's ordered now, there is no guarantee that we'll see it being ordered in future. Essentially, our database engine will just pick any means to store our records so long as it sees as sufficient. Now, what I have here is just a few records from the table that we saw just now. And through the use of a clustered index, our database engine would traverse this tree as follows. So each page stores ordered records. And at the top of each page is the record with the lowest values. This clustered index is on our ID over here. And so the keys stored in the intermediate and the root node consists of values from that ID attribute. So from the root node, consider we're trying to find the value of 3. From the root node, we understand that 3 is greater than 0. So we continue going down the node. You see 3 is less than 4. So we don't consider the intermediate node associated with this key, which allows us to go left. Sweet. 3 greater than 0. Okay, so we know we go down this intermediate node. And we see that 3 is greater than 2. That enables us to go to the leaf node associated with this key. Sweet. Now, indexes are really easy to create. I mean, like really, really easy. I've been using them for years, even though I didn't know what they were. And the reason why I say that is because clustered index are created as soon as you use a primary key constraint. Similarly, a unique constraint results in the creation of an index. So that's exactly what I'm going to do now. We have the table scores. We look below, doesn't have any indexes. Cool, no stress. We'll simply create a primary key, which will result in the creation of an index. Okay, sweet. There we go. Cool. So our primary key is created, and we refresh our Object Explorer to find that in the scores table, take away database, tables, an index has been created, a clustered index in particular. An alternative index follows the same implementation. It's called a non-clustered index. The only difference between the two is that the clustered index defines how our database is stored on the disk, whereas a non-clustered index is a separate file that's used for optimized selection of records. Yeah, furthermore, a clustered index, a table can only support one clustered index, whereas a non-clustered index whereas a table can have many non-clustered indexes. Okay, cool. So I'm quickly going to take a moment to go through an execution plan to show how indexes are used. There we go. Sweet. So we have a clustered index on our ID. Boom. And when we execute a query over here and click on this execution plan button, run the query, we see an execution plan, which is read from right to left, top to bottom. And as we hover over this item here, we have two very important items: the number of rows read and the actual number of rows for all executions. The number of rows read indicates how many rows were loaded from the disk in the execution of the query, whereas actual number of rows for all executions indicates how many records was returned. So essentially, using this index, as we perform the query, we only took one record from the disk and returned one record from the disk, which is amazing. You can't get any more efficient than that. That's all you ask for. That's what we want over here. Now, alternatively, if I run the same query on another attribute that does not have an index, such as score, I don't know. Yeah, cool. Run it. Check out the execution plan. We have an index scan. Now, the scan operation is when you iterate through the leaf level of the tree, should you have an index. Alternatively, this is where you are iterating through each record in the table to ultimately find the record that you need. Now, if we hover over this again, we see that the number of rows read from the disk is 501. And the total number of rows returned from the query is 26. Now, this illustrates the inefficiency in not using indexes. Okay. Cool. So now that we've identified how indexes are useful in the execution of queries, let me conclude this talk by quickly running over some of their disadvantages. So, as the clustered index stores the pages of our table in physical memory in the leaf section of the binary tree over here, all manipulations made to our table results in us needing to reorganize our clustered index. And as non-clustered indexes, use these keys from the clustered index to refer to our records on our disk. Making manipulations to our table will result in quite a bit of overhead in terms of memory usage. Furthermore, indexes are susceptible to fragmentation, which may have a negative impact on the performance of queries. Yeah, thanks for listening to my tech talk.